All right, so we're going to head into chapter 2 and start talking a little bit about derivatives. Now, everything we've done in chapter 1, all of the finding limits, is really set up for being able to find derivatives. So, first of all, the tangent line problem. This is like one of 4 major problems or 4 major really kind of discoveries, I guess, in the mathematical world in the 17th century. And you can look up all kinds of interesting history, especially on YouTube, and getting stories about like feuding mathematicians trying to outdo each other and solve these different problems. So it's pretty interesting. Anyway, what was the problem? Trying to find the slope of a tangent line at point P, because we know that if we have 2 points, a secant line, if we have 2 points, we can find the slope between any 2 points, and that's our difference quotient from last year and the year before. But if we want, rather than having a secant line, if we want the slope of a tangent line, which you'll see the importance of that as we go through this, we have to figure out how to do that. So we can try to make delta x, the difference between the 2 points, just really, really small, and we use limit notation to accomplish that. So the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. If we take the limit of that, then this gives us an equation for the slope of a tangent line. So let's write that down. This little limit notation, allowing delta x to approach 0, this is an equation, because it's not always going to come out to a numerical value, an equation to find slope of a tangent line. And when we say a tangent line, we mean a line tangent to f of x at some value of x. So again, this is a really pretty much half of our year is dedicated to derivatives. So the derivative, it's the derivative of the point is the slope of the tangent line at that point. And we have all kinds of different notation. Part of the reason there's a lot of different notation, some of it is just shorthand, but also different mathematicians, as they were, inventing calculus, for lack of a better word, they use different notation. And so, we have a couple of different ways to look at this. So really common is f with this little tick mark. That's not a 1, that's a tick mark of x. It's read as f prime of x, and it means the derivative of f of x. So again, the slope of a tangent, the equation for the slope of a tangent line at whatever point x we're talking about. Another really common is dy dx. It looks like a fraction, dy over dx, but it's just read dy dx. It means the derivative of y with respect to x. And all that means is you have some equation, y equals, and it's in terms of x. If you flip those, if it were dx over dy, it would be the derivative of x with respect to y. So the equation would be x equals, and all of your variables on the other side would be y. Sometimes we drop the x. F prime means the same thing, derivative of f. And sometimes instead of dy dx, instead of y, the function, it might be called f of x or something else. So d f of x dx, derivative of f of x with respect to x. All right, so all of that means the same thing. So dy dx is the same as f prime of x, which is the same as the limit as delta x approaches 0 of the difference quotient. This is our limit definition of a derivative. On the AP test, on our quiz on Wednesday, you're going to be asked to find the derivative of f using the limit definition of a derivative. So you'll have to show me this limit work, which is what we're going to practice today. Again, what does all this mean? It's the slope of the tangent line at x. It's the equation for slope, we should say. It's also the derivative at x. It means the same thing. Derivative means slope. That's one thing you should have tattooed onto your brain somewhere. So So let's put this into practice. Find the derivative of f of x equals x cubed plus 2x. Now, people who have had calculus before, or even physics C, you're not allowed to use the derivative shortcuts yet. We'll get there. That's the best day ever. But for now, we're going back to the limit definition. And why? Because you will be asked to use that on the AP test. You have to remember how to do it. Here's the thing. Don't drop limit notation. Just like we had in chapter 1 leading up to this point, you're not allowed to drop limit notation until you actually sub in use direct substitution. So f prime of x, the derivative of f of x, is equal to the limit as delta x approaches 0 of x plus delta x, of f of x plus delta x minus f of x all over delta x. Now, do you have to write this formula every time? No, I'm doing this for the notes, especially for our first one. You can jump right to the next step, which would be go ahead and write out what is f of x plus delta x minus f of x. So limit as delta x approaches 0, plugging in x plus delta x in for the x's, you would get x plus delta x cubed plus 2 times x plus delta x. We're supposed to subtract f of x from that. Remember, subtracting f of x means you're subtracting every term. It goes in parentheses, or distribute the negative through right away. And then it's all over delta x. And then we got to cube out a binomial. Now, I don't know if you have this memorized or not. I often don't remember exactly the how we cube out a binomial. So sometimes I do it the long way. Multiply it out first, like this. Gosh, try to multiply it out correctly. That's squaring it, and then multiply it by another delta x. Or I am cheating a little bit. I did do this ahead of time. So there is a formula to cube it out, which is the first term is cubed. The second term is plus 3 times the first term times the second term squared, plus 3 times the first term squared, times the second term, plus the last term cubed. This one's not hard to remember, but it's with the subtraction. I always mix up which one's minus. I guess it would be this one's minus. Anyway, I'm going on and on. So, all right, so we cubed that out. Distribute the 2 through. Plus 2x plus 2 delta x. Distribute the negative through. Minus x cubed minus 2x. All of that, don't forget, is over delta x. Now remember your difference quotient work from pre-calc and math 3. It should work out, if you've done the math correctly, that all of the non-delta x terms cancel out. So x cubed minus x cubed, gone. 2x minus 2x, gone. And since every term has a delta x in it, I can divide by delta x. I still have my limit notation for one more step. So the limit as delta x approaches 0 of just 3x delta x plus 3x squared, that delta x canceled, plus delta x squared, and don't forget this guy, plus 2. Finally, I can do direct substitution because I no longer have a delta x in the denominator. When you plug in 0 for delta x, this term was gone, this term's gone, you get 3x squared plus 2. Now, those of you who know let's clean this up. F prime x, therefore, is 3x squared plus 2. And those of you who remember the derivative shortcuts, if you're just using your derivative rules, yes, this would be 3x squared plus 2. So you can kind of check your work that way if you're lucky enough to have been exposed to this ahead of time. Remember, what is this again? This is a formula for the slope of a tangent line to f of x at any x value. So if I want to know, okay, well, what's the slope of the tangent line at 4? It would be 3 times 16 plus 2, which is what, 50? So, yeah, so kind of handy. All right? Find dy dx for y equals square root of x. Then find the slope of the graph of y at 1, 1. So let's find dy dx first. Remember, this is the same thing as find the derivative. So dy dx is equal to the limit. Instead of using delta x, let's switch it up to, let's use h. Limit as h approaches 0, just so that we've seen different things. Instead of writing out my formula, I'll write it over here, but f of x plus h minus f of x over h. I'm going to go ahead and just plug in the x plus h. So square root of x plus h minus square root of x all over h. All right, that's a much shorter equation, right? We can't do direct substitution right now, but you should be in the habit of seeing radicals in your numerator and multiplying by the conjugate as a way to work on this so that direct substitution does work. Okay, keep your limit notation. The limit as x approaches 0, or as h approaches 0, of x plus h minus x over h times square root of x plus h plus square root of x. Remember, your x terms are going to cancel. H divided by h is going to be 1. So let's write one more line before we direct substitute. This is simplifying to limit as h approaches 0 of 1 over square root of x plus h plus square root of x. Use direct substitution to put 0 in for h. You have 1 over radical x plus radical x, which is 1 over 2 radical x. So dy dx is equal to 1 over 2 radical x. Evaluate this slope, or find this slope at 1, 1. So the only thing I need from this is the x value. This is saying, here's a way to write that notation. The derivative dy dx evaluated at the point 1, 1. That little line, vertical line there with the point down here, is a nice shorthand way of saying I'm going to plug that in. Of 1 over 2 radical x would equal 1 over 2 times square root of 1, so 1 over 2. If we were doing function notation, it would just be like f prime of 1 equals whatever. But here we have this little notation. So if we're given a point, we can find the slope of the tangent line. And then if we have a point and a slope, what could we find? Point, slope, form of a line. Remember point slope form? Y minus y1 equals m times x minus x1. Here's the great thing about calculus. We want to be lazy with it, and we're just going to leave our equations in point slope form unless it makes sense for some reason to change them otherwise. Like in past classes, we've switched, solved for y and got it into slope intercept form. What line are we talking about? The tangent line. Okay, so f of x is 4 over x plus 2. Find the equation of the tangent line when x equals negative 1. First thing is find f prime of x. This is, actually I want to categorize this. This is going to be our work on the slope. You don't have to do this for the AP test, but kind of nice to organize what you're doing. Let's find the slope first. F prime of x is the limit as x, not x, we'll use delta x. As delta x approaches 0 of 4 over, you're plugging delta x into this, x plus delta x plus 2. I'm sorry, I misspoke. You're plugging x plus delta x into that. Minus f of x all over delta x. That is an ugly complex fraction, so I want to work on it by multiplying by the LCD. X plus delta x plus 2 times x plus 2, top and bottom. Next line, don't forget limit notation. Limit as delta x approaches 0. Okay, so this top fraction would become 4 times x plus 2. Second fraction would become minus 4 times x plus delta x plus 2 all over delta x times x plus delta x plus 2 times x plus 2. Limit as delta x approaches 0. All right, what will we have here? I don't want to write a whole new line, but I am going to write off to the side 4x plus 8 minus 4x minus 4 delta x minus 8. 4x's cancel, 8's cancel. You just have minus 4 delta x over delta x plus delta x plus 2, x plus 2. Delta x is canceled. We can drop our limit notation since we're using direct substitution, and we have f prime x equals negative 4 over x plus 0 plus 2, so x plus 2 times itself, x plus 2 squared. All right, this is our formula for slope. What is the slope when x equals negative 1? So f prime of negative 1 equals negative 4 over 1, so negative 4. Okay, to write an equation for a line, you need a slope. We have it. You need a point. We know x is negative 1, but we need the actual ordered pair. So we also need to know what is f of negative 1. Back to the original function, plug negative 1 into there, you get 4 divided by 1, which is 4. So using the point negative 1, 4 and the slope negative 4, the equation for the tangent line is y minus 4 equals negative 4 times x plus 1. There are times when a derivative doesn't exist. And so there are basically 3 cases where a derivative doesn't exist at C. And let me see, do we have this? I want to make a note up here. It appears throughout the packet, but when a limit doesn't exist, I'm sorry, when a derivative doesn't exist, no derivative, the term that we use for that is not differentiable. You'll see in the AP test and you'll see on Wednesday's quiz, define points, if any, at which x is not differentiable, and then explain why. Okay, so what's one case? A derivative can't exist at C if the function is not continuous at C. And remember, we have several ways that a function might not be continuous. There could be a jump in the graph, like a piecewise function, some sort of break in the graph. There could be a vertical asymptote, where, who knows what's happening. There could be like a hole with a point up here, something like that. So a hole in the graph, a break or a jump in the graph, a vertical asymptote. If the graph is not continuous at C, should write a little C there, then it's not differentiable at C. It's differentiable everywhere else, just not at the places where it's discontinuous. Case 2 would be if the function has a vertical tangent at x equals C. So a classic example of this is like a graph that kind of looks like this, where your slopes are like nice and shallow. They're getting steeper, steeper, steeper. The turning point to switch concavity or which way the curve is going is right there at 0. So that vertical tangent right there, vertical tangent, that would be our C value, not differentiable. The function has a sharp turn at C. So the sharp turn thing means your slopes are supposed to gradually change from one thing to the other, but think of an absolute value graph. The slope could go from -1 to the left of C and then to positive 1 to the right of C, and there's no changeover. There's no transition where it goes continuously from -1 to 1. It just hops to the next one. So that derivative wouldn't exist. Another sharp turn example is like it might be curved, something like that. So at that point C, not differentiable. What if we're not looking at a graph? To look at this analytically, we might want to look at alternate definitions of a derivative. So this is useful if you're looking at some sort of relationship between continuity, differentiability. So if I put everything in terms of C, let's say C is the distance between the 2 points on the curve of a secant line, and we're trying to let C approach 0. So as x gets, I'm sorry, C is this other point over here. So as x gets closer and closer to C, the difference between those 2 points would become close to a tangent line. All right. Limit as x approaches C of f of x. This is an equation, whatever the equation is, minus f of C. F of C is plugging in C. That's a number. Divided by x minus C, which again will be a number. What would this look like? Find f prime of 1. If f of x is x plus 3 over x minus 1, first I want to see, is the function differentiable at 1? So does f of 1 exist? I'm kind of running through these 3 cases. Does f of 1 exist? No. You get 4 over 0. So since f of x is not continuous at 1, there is no derivative at 1. So f of x is not differentiable at x equals 1. Why? Because f of 1 equals no solution. And that's what I would write on my AP test or on my quiz on Wednesday, whatever. Case 2, can I plug 0 into this function? Does f of 0 exist? F of 0, remember, to the 1/3 power means cube roots. Yeah, f of 0 exists. This is continuous. All right, so let's use our, let's jump in to use our alternate definition here. So what about f prime of, instead of C, I'm going to write 0. I don't know what this little squiggle is. So it's f of x, x to the 1/3, minus f of 0. I'm going to write f of 0 right there, over x minus 0. Oh, what's the super important thing I forgot? Limit as x approaches 0. Sorry. So it's the limit as x approaches 0 of x cubed minus 0, so I'm not going to write that, divided by x. And it's not x cubed. Sorry, guys. It's early. X to the 1/3 divided by x. Limit as x approaches 0. Oh, we can simplify that a bit. How about 1/3 minus 1 would be 1 over x to the 2/3, just so we don't have x's in the top and the bottom. If I try direct substitution on that, I get 1 over 0. Okay, so that's showing me that limit doesn't exist. In what way does it not exist? Well, if I'm getting 1 over 0, this means that the limit as x approaches as x approaches 0 of 1 over x to the 2/3 equals infinity, because you're plugging in 1 divided by some really teeny tiny number. Even if that teeny tiny number is negative, remember it's getting squared and then taken the cube root of, so it's going to be positive no matter what. It's going toward infinity. So f of x, let's write this. F prime of 0 does not exist, is no solution, because the limit as x approaches 0 of 1 over x to the 2/3 equals infinity. There is no derivative at x equals 0. Our last one, does f of 3 exist if I'm supposed to find f prime of 3? Yep, it equals 0, so it's continuous. think about this graph. You don't have to always use the limit definition. Think about this graph. It's got a sharp turn at 3, which is the vertex. So you could stop right here and say f of x, or f prime of 3 does not exist, or f of x is not differentiable at x equals 3 because there's a sharp turn at 3. What if I wanted to use this, though? If it said use a limit definition, so f prime of 3 equals f of x minus f of 3, which is 0, over x minus 3. Why do I keep doing that? The limit as x approaches 3. Gosh. You can see a common mistake as you're going through this. I'm making it all over the place. Hey, this is something we keep having in chapter 1. What is the limit as x approaches 3 of this little split piecewise function? Remember this graph? It looks like this. Oh, that limit doesn't exist at 3. Okay, so the limit as x approaches 3, I can call this f of x is not equal to, on the left side, is not equal to the limit as x approaches 3 on the right side of f of x. Or again, think about the graph, talk about the sharp turn. Okay, one more example. Find f prime of 3. Does f of 3 exist? Yeah, it's 9 minus 4 is 5. Okay, well, f prime of 3 equals the, I'm going to remember this time, the limit as x approaches 3 of f of x minus f of 3 divided by x minus 3. That equals the limit as x approaches 3 of, now this is going to be x squared plus 9. I'm sorry, x squared minus 9. When you factor it, the x minus 3's will cancel, and it will simplify to x plus 3, which then you can use direct substitution on and get 6. Okay, so finally, we get one where this works. F prime of 3 is equal to 6. And again, if you know your derivative shortcuts, you can double check your work here. The derivative of this is 2x, and 2 times 3 is 6. So those of you who haven't had the shortcuts yet, you can see how much faster that is. We have to get through this stuff first. Okay, so summary. F of x is not differentiable at x equals c if either it's not continuous at c, or you have a vertical tangent at c. And when we used our limit definition, that was when the limit turned out to be infinity or negative infinity. Or if you have a sharp turn, and believe it or not, that's the terminology we're using, at c. Now be careful though, just because something is continuous at c doesn't mean that it's definitely differentiable. So like, because for example, cube root of x is continuous everywhere but not differentiable. Absolute value x is continuous everywhere but not differentiable. So those are just two examples. But if you know that a function is differentiable, then it's guaranteed to be continuous. Because if it's differentiable at a value of c, it has to be continuous at c, otherwise it doesn't work. All right. This is actually a really important thing to keep straight. They'll try to throw that into multiple choice and things like that. All right, that's it for today.